Okay, well, we are about ready to start our webinar for today. So to make sure you're at the right place, you are at the webinar, How to Reduce Your CMM Programming Time Up to 95%, sponsored by Mitutoyo. So if your company has a CMM and you do your own part measurement programming, then you know how often many hours can go into developing a part program. And of course, this delay, these hours can cause production cycles to be held up. But if you have software that works directly from a model-based definition to automatically create your part measurement program, you can drastically decrease the programming time. And in fact, as we're going to see, you can decrease it from several hours to just a few minutes. That is the subject of today's webinar, using software to automatically create your part measurement program. Before we get into the webinar, just a reminder, at any time you can send questions to us using the Q&A box. If you don't see it, you should be able to click the Q&A button at the top of your screen. There may be a little drop-down menu up there. If you just mouse over it, you'll see a Q&A button. Click that. Please use the Q&A box to ask your questions and not the chat box. It's the Q&A box that we actually monitor. A recording of this webinar as well as a copy of the slides, a PDF copy, will be available one day after the webinar. We'll send you an email on that. So let's get started. Our presenter today is Larry Maggiano, Senior Systems Analyst at Mitutoyo America Corporation's headquarters in Aurora, Illinois. Larry has an extensive background in dimensional metrology and is particularly focused on advanced CAD to CMM metrology processes. He's also a member of ASME Y14.41 and chairs the Dimensional Metrology Standards Consortium, the DMSC, Quality Measurement Directives Working Group. In other words, Larry is your go-to guy for CMM automation. So let's get started. Go ahead, Larry. It's all yours.
Thank you, Dirk, for that excellent introduction. And thank you, everybody who's attending this webinar. We hope to answer some questions about model-based inspection and more specifically about how Mitutoyo's MiCAT Planner can address that model-based inspection workflow. As I was saying, MiCAT Planner changes the relationship between people and precision measurement with one click, and we'll talk about that today. Before we get into the nuts and bolts of model-based inspection, we've got to go through and define some, as the military would say, TLAs or three-letter acronyms. I'll be using these throughout the presentation. The first one is model-based definition. It's also, you heard the term design model or CAD model with PMI, but MBD is the term of choice that we hear most often here in the USA. With MBD, it's model-based manufacturing, and I'm sure that's self-evident in terms of what that is. The next one is model-based inspection. So these three, MBD, MBM, and model-based inspection, are the primary model-based terms that we use for what might be called model-based environment or model-based enterprise. PMI is another term that you'll hear. It's product and manufacturing information. It's also that annotation in GD&T, and we'll talk about that in just a bit as well. So the last of our TLAs is DME, and DME is a term that encompasses all of dimensional measurement equipment. And these terms are going to be used throughout the webinar, and we'll go from there. Let's talk about MBDs first. What are they? So let's define an MBD. MBDs include PMI, which are visible dimensions, tolerances, notes, text, or symbols. I'm sure most, if not all of you, have seen this kind of annotation on a 2D drawing or 3D CAD model before. MBDs are specifically used or created by design engineering, but their use is by manufacturing and inspection. Go ahead. There's a question. Please interrupt me at any time, Dirk, and I'll try to make sure that I answer questions as we go along. There is something called MBD standards that I wanted to bring up as well. The two that are probably the most prominent general standards are ASME Y1441, Digital Product Definition Data Practices, and MIL Standard 31000A Technical Data Package. So if you want to have more information about what an MBD is and some references and guidelines, I would steer you to these two standards as well as others that are available for MBD. There are two kinds of PMI, and this is a critical topic for MBDs. The first kind of PMI is presentation PMI. It visualizes the PMI for the person. It essentially, and I'm sure you've all have seen this before, creates a three-dimensional drawing. And it may be organized by CAD views, by views in the CAD software. The other one is called representation PMI. It complements presentation PMI. So you have these two terms. The first term is the visualization for the person. The second term is for the consumption by the software applications and the generation of the MBD by the software applications. It's also known as semantic PMI. And this is, as I said, is what enables model-based inspection. This is a very interesting note from Joshua Lubell at NIST. He states, unambiguous representation and presentation of PMI are critical for the digital product definition. In other words, we need both for the machine and for the person. They need to be there, they need to be synchronized, and they need to be complete and unambiguous. And those are considerations when a CMM might use an MBD for model-based inspection. There's a process, there's a journey that I think all of you would recognize here as we go along. And the journey is we all started off in a drawing-based workflow where the 2D drawing is the master. There's an intermediate process, a model-centric workflow where the 2D drawing is the master and the 3D model provides part geometry. This is probably the most predominant workflow now as we move from drawing-based to model-centric. But we're moving further to a model-based definition workflow where the 3D model with the PMI is the master. So you can see a strict, a progression from drawing-based to model-centric to model-based definition. And we'll be addressing really the second and third of these, model-centric and model-based definition, in today's webinar. If you want to know more about this journey, this is a reference that you might want to go to. It's at the Model-Based Enterprise website, and it's an assessment tool that you can take for your company to see where you are in this progression to model-based workflows and model-based enterprise. A little more technical detail about MBDs. MBDs are the core geometry and the core PMI that we need for model-based inspection, but we also need something called supplemental geometry in some cases. And this supplemental geometry communicates design requirements, but is not intended to represent a real part feature. Here are some examples of supplemental and bolt circles. So the model is this geometrical object. We have this two kinds of PMI, and then we have the supplemental geometries that helps us manufacture and inspect the part. Questions before we proceed? Dirk, anybody about model-based?
No, I don't think we have. Well, actually, here's a question I have. Let me just throw this out. As we're talking, I was wondering, why is PMI actually needed? I mean, maybe your CAD files already have your dimensions and tolerances all worked in there.
Mm-hmm. Good question, but PMI is actually the dimensions and tolerances. So the GD&T that you see, the notes, the annotation, that's all part of this larger umbrella called PMI. So PMI is necessary, and then certain kinds of PMI are essential for model-based inspection. And you can see these three CAD models, and they all have GD&T, which is a type of PMI, and this is the kind of MBD that's necessary for model-based inspection.
I'm not super familiar with all this, so maybe some of our attendees aren't either, but is PMI a separate I don't know, something that's embedded inside the CAD file, or is it simply, like, suppose they just had their CAD file just marked up with GD&T stuff. Is that the same as having this information embedded in PMI?
Yeah, I understand that distinction. As I said before in a previous slide, there's two general categories of PMI. One is presentation. This is the markup, the visualization that we see as humans. But the other one is called representation, a little bit trickier to understand, but it's how the PMI, how the features and characteristics are linked to the underlying geometry in the 3D CAD model. So both kinds of PMI are needed, and it's essential that semantic or representation PMI is available to facilitate model-based inspection.
Okay, so what we're talking about specifically today is not the visual representation, but that this representational element that you're talking about. That's really what the automation would need going forward. Is that aspect of it? Is that correct?
That's correct for the automation, but we want to make sure that the human is always in the loop and supervises and monitors and audits this. And the only way that they can do that is to also have presentation PMI, so that they can confirm that the two kinds of PMI are exact and work together.
Okay, perfect. And just a reminder before you go on, Larry, if anybody else has questions, feel free to use the Q&A box to send your questions to us. You can just, if you don't see the Q&A, just bring your mouse to the top of the screen. There should be a pull-down menu, and you can select Q&A from there, or you might see the Q&A box in the lower right corner of your screen. So go ahead, Larry.
Great, thank you. So let's go a little more in detail about what's required for model-based inspection. We must have a particular kind of CAD model. This is called a BREP model. There are other kinds of CAD models, surface models and mesh models, wireframes, but for today, in today's world, today's technology, the BREP solid model, that includes semantic PMI. Of course, also the presentation PMI is the requirement. We need what's called a virtual DME. This is a virtual process where we take information that's virtually designed as a CAD model and use it with a virtual DME, dimensional measurement equipment. But obviously, to inspect the real part, we need the physical, actual CMM as well. We also need, especially for automation, a measurement plan that contains rules and settings. And last but not least, we need the MiCAT Planner, of course. So moving on, let's take a look at each of these categories. Dimensional measurement equipment. Model-based inspection is most often used with CNC DME. CNC are automatically programmed machines and automatically executing machines. It can be done with manual machines, but the biggest benefit, though, is with CNC DMEs. The most common CNC DME is the coordinate measurement machine, aka CMM. I think we've all heard of these machines, and you can see some of these in the Mitutoyo slides here, and we'll talk about these in a little bit as well. And just to let everybody know that it doesn't have to be a new machine. Most current as well as new Mitutoyo CNC CMMs support model-based inspection, but they must have the additional option of the MiCAT Planner to enable this model-based inspection workflow. Okay, we'll move forward. Now we're getting down to some really interesting technology here. These are sensors for model-based inspection. And sensor selection plays an important role when matching rules and settings to features and characteristics of the MBD, or binding, to use that term, the sensor and the feature and the characteristic. The feature is a cylinder, the characteristic may be cylindricity. Now, what particular sensor do I use in a model-based inspection workflow that's most appropriate for that feature and characteristic? We support, for our model-based inspection workflow, these kinds of contact scanning, very common sensors, as well as touch trigger sensors. And I'm sure you've all seen these before on typical CMMs. Now, what kind of CMMs does Mitutoyo offer that support model-based inspection? We have bridge machines. That's probably our all-around workhorse for parts and assemblies. We also support horizontal machines, and we also support shop-hardened gantry machines as well. So you see two examples of vertical axis machines. One is a typical workhorse, and one is actually used for inline or nearline production. What other CMMs do we have available for model-based inspection at Mitutoyo? We have also shop-hardened horizontal arm machines as well. And last but not least, the change racks, modules, and styli all contribute to this virtual DME, virtual CMM environment that enables model-based inspection. Now, that was a pretty quick overview of Mitutoyo's hardware and CMM and DME technology in general. But the key thing is we have a virtual CMM that's used in the model-based inspection, planning, and program generation phase. And then we have actual CMM that's used in the execution of that program that was generated in the model-based in the initial model-based inspection workflow. Might anybody have any questions about that before we proceed?
Yeah, there's a question. Maybe this is, I think, still a spinoff from kind of a question I asked earlier. Is the GD&T we see, and I think I'm reading this right, is that created in a CAD system? And I believe we already said that was the case. So
that's the most common case, that the model-based definitions and the GD&T are created in CAD. But, and we'll see that a little bit later in the webinar, there may be no GD&T on the CAD model, and we do have a way to actually measure the part without GD&T, as well as add GD&T to the part as well, because that situation exists very commonly as well, Dirk. So yes, both, okay. All of the above.
Okay.
And we'll take a look at that. So now what is the MiCAT Planner? I mentioned the MiCAT Planner is an important part of model-based inspection. It's a measurement program software from Mitutoyo that enables one-click automated generation of CNC CMM programs. And, you know, it's the last piece of the puzzle that really makes model-based inspection practical and worthwhile. Mitutoyo's been in a feature-based CAD world for quite some time, but moving forward into model-based really takes it into the 21st century. There are some upstream activities that need to be considered, as we talked about earlier, to support the MiCAT Planner's model-based inspection solution. Where do these models come from? They may not come from a CAD system. They may come from a CAM system. They may come from some other software application. But who's doing the 3D model and how are they doing the 3D model annotation is something that needs to be considered. Now, that's overall beyond the scope of this webinar today, but it's something as the downstream users, as we call ourselves, of model-based inspection, we need to know where these models come from and who did the annotation, just to make sure that we understand and the software understands what it needs to do. There are procedures, then again, which are beyond the scope of this webinar in terms of how these models are handled. Also, how are these models validated? That's an interesting and very important question as well. And finally, something that needs to be considered by any corporation or by any user of model-based inspection is what are the rules, what are my best practices? Any CMM programmer who's done this for a while has rules of thumb. There may even be documented procedures. This is what we do when we measure this feature with this characteristic. So the MiCAT Planner really is best used in a rules-based environment. If you don't have rules, the rules can be easily generated, as I'll show you later on. This, I think, will tie it all together for a lot of us. Here, it's the MiCAT Planner model-based inspection workflow. And the thing you see in blue is the MiCAT Planner, and it starts off with defaults and intelligence. These are things that are built into the planner, or these are settings that are defined in the planner and basically set up a smart environment for the MiCAT Planner to operate with the DME and with the MBD. And we'll detail these in a little bit as well. User parameter settings. I want to do this, and I want this to stay in this state in the planner until I tell you otherwise. All software has parameter settings, and the planner uses these settings and retains these settings, so it customizes and adapts to how and what you want to do in terms of program generation. Another key issue, another key that, and we'll see this in its power in a little bit, is user-defined rules. We provide, if you will, a starter kit. It's just a default, but the rules themselves really enable this automated and optimal generation of CNC CMM part programs. Now with that, and we talked about this, is the MBD. This is the typical MBD, as you can see, and it has, and I can assure you that this is both correct for presentation and representation, in that both are contained in the MBD. As we talked about, Dirk, we need both, and they need to be the same. We don't want to have presentation and representation different. We need to, of course, add to the mix a configured virtual CMM. In this case, you can see one from Mitutoyo, and in our MCosmos software, we have something called the CMM System Manager, and this is something that can define just about any CNC CMM that we've made or are making today. When these technologies, and I'll call them that, are mixed together, the MiCAT Planner automatically generates a measurement plan. It reads the model, it reads the defaults and intelligence, it reads the setting, it reads the user-defined rules, and it reads the DME, the CMM. And it matches intelligently all of these various aspects of model-based inspection workflow under a single structure that allows synchronous and automated generation of a program from an automatically generated measurement plan. This next step, and this is this one button click, we generate a measurement plan, we generate a measurement program, and we then, if you will, post it, or translate to another terminology, to MCosmos GeoPack, and the part manager receives this program, and this is the, if you will, the operating system of the CMM that understands the part program, analyzes the geometry, moves the machine, and reports the results. And it's part of the MCosmos suite, and MiCAT Planner is an automatic part program generator for the Mitutoyo MCosmos program. That's it in a nutshell. Dirk, do you have any comments on this workflow, and does this explain some of the big picture ideas?
Yeah, kind of one quick question I had is you mentioned bringing this in from CAD, but you haven't really specified what CAD file formats that you support. So what can we bring into MiCAT?
The file formats that we support, and we'll define these again a little bit later, are the Siemens PLM NX file format, the Dassault Systems CATIA V5 file format, the PTC Creo Pro Engineer file format, and also the ACES file format, though the ACES file format does not contain PMI. The three previous file formats from those CAD systems may or may not contain PMI. They may or may not contain semantic PMI, representation PMI. And I'll show you an example of that in just a second and how we can handle those cases. So those those three CAD systems plus the very common ACES format as well is what the MiCAT Planner can read and import. Thank you, Dirk.
Okay, thank you.
So defaults and intelligence, what is that? Well, these are the series of, as you can see, the left-hand column, basic settings. This allows, by the way, deployment of the planner throughout a global enterprise. You can see Spanish, Portuguese, Japanese, Italian, German, French, two kinds of English, and Chinese. This may be very important, for a large company that might have facilities in other parts of the world, and they want to have a, consistent and optimal way to be able to program parts and sub-assemblies that are made overseas and bring them in, or even within a far-flung enterprise within the USA as well. Display format. This allows one to set up how many decimals to see the length, angle, vector, speed, and it ensures that the display requirements for different parts of various manufacturers can be modified easily as needed. The next one are project settings. You know, what you see here, these are, we talked about some simple out of the box. They're not simple, they're very smart, but I guess you would call them simple. I'm simple, but I'm not smart. These are touch trigger templates and contact scanning templates. And these make it easy to have a starter kit to say, well, here's what I want to do, here's what I start with, and here's where I want to go. 3D view settings, maybe I don't like the green for my first measurement point or red for my last, you can change them here. Translator settings, these are settings that are applied when one generates a GeoPack part program. Design model import settings. This goes back to your question, Dirk, about, well, what kind of CAD file formats can I import? And you can see some options here as well. And those are the settings, and now we're going to look at program generation options. These program generation settings are for tool selection, for characteristic evaluation order, part placement, uncertainty in the CMM, and runtime reduction. These are collision avoidance settings for clearances and moves. Very simple, a little graphical illustration of what they do, and very powerful, by the way. And finally, as our friends in the CNC CAM world might want to say, feeds and speeds. These are settings for measurement speeds and for approach and retract and measurement lengths. So those are settings, and they're a powerful set of parameters that one could easily modify as needed. But the real superpower here comes into these user-defined rules. This is the MiCAT Planner Rules Editor, and the Rules Editor establishes rules for features and characteristics. And we capture the best practices, whatever those are, it's not for us to say, for optimal inspection and consistent results. And these rules, you know, they can be specific to a part, to a family of parts, or to a company. And I've seen now a lot of companies starting to evolve in a general set of best practices. Here's how we do this, and here's what's worked for us well in the past. All of this information can be captured and applied automatically through the Rules Editor. And you can see the Rules Editor is very conversational. I mean, I can understand it. It's not some complex programming language. It is, if this, then do that. And I'll detail that on the next slide. So you see in this particular case, we have on the very top something called criteria. And if you can't read it, I'll read it for you. Criteria for an inner circle measurement with a radius of less than or equal to 9.999. It's the if-then part of the rule. It's criteria. And the then part of the rule is actions. And by the way, there can be one or more criteria, and there can be one or more actions. And the actions define the parameters to be used for measuring all circles in the design model that meet that criteria. That set of criteria, that set of actions are contained in that one rule that's highlighted. It's the circle measurement in contact scanning mode. So the box on top is criteria. The box on the bottom are the actual specific actions for that rule. Very powerful, and we think very complete. Maybe not 100% complete, but we spent a lot of time providing a rule kit for our customers to be able to define rules, edit rules, delete rules, add rules, and selectively and collectively for any MBD and any DNE. Let's look at an example of how to add a rule. a little video you can see. And we're highlighting cylinder measurement in scan mode. But we're going to add a feature here. And you can see how quickly and easily it is to add default values for that. So feature equals cylinder, actions equal measure false, fitting method mean, minimum zone, minimum circumscribed, etc. Sampling method touch trigger. And you can actually do it quicker than I can talk. And it's a very quick and easy way to define any new rule that you want to implement in the MiCAT Planner. Number of lines, points per line, and it's all context sensitive. So if we're using contact scanning versus touch trigger scanning, the rules themselves are applicable, and it gives a pretty good indication of how you might want to use, in this case, scan mode, the scan parameters associated with the contact scanning. Changing scan pitch. The X on the right-hand side says delete a rule. Delete an action, is a part of a rule.
And Larry, can you get a little bit closer to your phone?
Sure. Sorry about
that. Oh, perfect. Thank you. No sweat.
So in this period of time, we've created a very powerful rule for measuring a cylinder using contact scanning. Now, the original rule set, the measurement plan that we invoked, was touch trigger. So you can mix and match as you need to between contact scanning and touch trigger contact. Filter type, none, Gaussian. And looks like we're finishing up here. And now we're going to close that up. And we've just saved that rule. So it's very powerful, very flexible, and it's what we provide to our users for editing and managing rules. Okay, we're going to now show you an end-to-end workflow in under 6 minutes that starts with models, with DMEs, and walks all the way through to part program generation and execution. We're loading a part. It's an MBD, I say part, but the model represents the part. And you see a three-dimensional model with semantic and PMI, as well as presentation PMI. We just loaded the virtual DME. You can see the DME configuration, all the tools available. And that plan in the plan view, that measurement plan, was generated automatically. Those red dots, those error messages say, well, I don't currently have a tool available for that particular feature. So we're going to look at it in the front view. Let's zoom in. Let's take a look at the model and let's see this. Maybe if we move the model up in the air, can we do that? Yep, we can. And we're going to say here centered in volume. We'll move it up. This will give the DME, the CMM, access to more features for parts. And it's, as soon as we say, okay, this is where I want to place this, I want to direct your attention back to the plan view. And now you can see it automatically recalculating what I can access with the available tools for that model with those features. And now all of a sudden you've gone from essentially half the features being measurable to all the features being measurable. That's the matching of the DME, the rules, the MBD within the plan. Very powerful process. Let's zoom in. Now, this is a one-click measurement program generation. So we're going from a measurement plan on the left-hand side to a fully defined measurement program in the program view on the right-hand side. We can now look at the path. We can display entity points, paths and points, selected points, all points, path. And these are ways to visualize the three-dimensional aspect of the generated measurement program. And we'll take a look at these now. So by clicking over here on Start, you see the CMM moves to that position. Now we're going to do a simulation and animation. We'll crank it up, hit the speed, and play forward. And as you can also see in that where the cursor is, it's also doing a time estimation as well. This is a fairly complex program from quite a few features and characteristics. You can see on the left-hand side, it's synchronous in the plan view and the 3D view and the program view. That's one of the key advantages of the MiCAT Planner is its simplicity and its always synchronized operation. So if you change something in the plan view or the 3D view or the program view, it updates the other views as well. And when you animate or simulate, then you can see all three views, providing a synchronous view of what the virtual CMM is doing. The simulation is not necessary, but it certainly is something that the human likes to look at and make sure it's doing what you expect it to do. Now we're posting. We're translating to GeoPack, and you see sample part complete. That was the actual post-processing. And here's the program that was generated. And this is in the GeoPack editor. This is the native execution engine for mCosmos. And you can see what was generated from that plan through the measurement process to the program generation option. So we've looked at it in the editor. Now we're going to do a virtual execution. I'm not hooked up to a CMM here in my office. I don't have one of those, though I'd love to have one. But I do have a virtual CMM, and that's what we're going to execute as well. And this proofs the program in a certain way, saying, yeah, logically, this will execute, and in that time, it also generates from the nominal information an inspection report. We're looking at it in the 3D view, and that's the three-dimensional element graphics of elements view of the execution of that part program. Now that was all under 6 minutes, and it's something that we're very proud of. It's not instantaneous in the sense that it takes zero time, but compared to old methods, we're moving at maybe a 95% reduction between what was done previously and what is being done now, especially if you look at a drawing-based method.
Yeah, Larry, I was going to ask that particular part you were doing. I mean, can you tell me how long might it have taken somebody to manually create that part program as opposed to the few minutes that it took to do it with this system?
We're guessing on the order of 4 to 6 hours at least. Okay. I'm pretty slow. It might take more for me, but yeah, it's hours, sometimes days instead of minutes.
For a super complex part, yeah. Okay.
Yeah. And especially as the part gets more complex, I think the benefits scale as well. It does require a PC. We're not running a supercomputer here. It's just our standard PC, but 64-bit and a suitable graphics card. Okay. Let's move on. So what are the tasks automatically completed by the planner? Well, part setup information is provided. I think you saw that in the first part of the program that was sent to GeoPack. Operator warnings, they're optional, on, off. Do I want to warn the operator when the probe is going to exchange a stylus in the probe rack? Positional moves are tasks automatically created. Measurement commands, measure this point, measure this circle. Sensor changes, all GD&T is applied. That's transferred as well, as you saw in the program, and all the way into GeoPack, where the GD&T that's associated with a feature is created in the part program and executed when the part program is run, and then inspection results reports generated. So we're pleased that we can offer this kind of capability to reduce what took hours to minutes. So one key issue now is how do you manage projects within the MiCAT Planner? And this is a video that will show. And we're going to say, okay, let's save this as a project. The project is everything. It's the DME. It's the associated MBD and any changes to the GD&T. It's the rules and settings. They're all saved as one structure. You don't have to be a rocket scientist to know that. How it works, it's just being done in the background automatically. So we just saved that entire project for that particular part, that particular DME, and that particular rule set. Now we'll say create a new project from default. So we're starting in default condition. But let's just go back and take a look and reopen that same project again. And we just saved. And you can see everything's being done. It's quite fast. And it goes back to the same state that was where it was when you saved it. So everything's saved automatically. We don't have to worry about the CMM, the rules, the settings, and then model-based definition. That's handled by the MiCAT Planner. Okay? And that's flexibility. That means a program can be automatically generated for most part features, or as you can also imagine as well, just a set of part features. And each program can be saved as part of a complete project. It also allows you to customize a project, maybe for a first article inspection, or maybe for an in-process production operation, or maybe for a final inspection from the same MBD. So the same project can be modified and resaved in a different project name that might be for final inspection as you worked from in-process inspection and from first article inspection. This term, and this goes back to what you were talking about before, Dirk, is associativity. And this is showing that we maintain associativity between features, between characteristics. You see that plane? And we can modify these, by the way, and I'll show you that in just a second. But these associative elements in the planner are maintained automatically. What point set am I using? So as I work, I want to look at an individual point. All of this is done. You don't see a lot of complicated GUIs and things like that. It's just there and it just works. You can see when we clicked on flatness here, it highlighted the flatness GD&T callout. So this associativity allows you to locate and view the relationships of the features and characteristics quickly and easily. So you can navigate through this fairly complex process without getting lost. Now, this is something that's very important as well. This is adding GD&T. What if I have a model that's just a geometry only, and what if I have a 2D print? Well, this is an example of how you can use the planner to add GD&T to a model. Selecting a feature and saying, hey, this is the plane. I think it's the plane, and the user is confirming, yeah, that's the plane. Now, I just said, okay, I've got a plane. What can I do with it? I can set that as a datum. Automatically set it as datum A or as any datum label as well. And as quick as I can talk, I just did flatness as well. Now we can add another feature. I can add this particular feature can be a circle or it can be a cylinder. Now I'm going to set that as datum. You can see the feature control frames pop and the datums pop as well in the 3D view. So I've done that now, and I want to pick another feature. This is it's a plane. Okay, what can I do with that plane? In this case, I want to add a characteristic, flatness again, and I'm also going to add perpendicularity. And so in that period of time, I've just annotated those three features with semantic GD&T, with datum labels, and I've got now a measurement plan that I created from a 3D model. I said, create a measurement program. In this case, I'm doing scanning, and we'll execute. So in about as quick as I can talk, which isn't very fast, but this thing works a whole lot quicker than I do, I've generated a part program from a 3D CAD model that had no GD&T. I'm still kind of amazed when I see this myself, and I've been looking at this now for a little bit of time. It's really a game changer. We're done. Now, if I wanted to post that and execute, and I had that part on the machine and was set up and oriented, I'm good to go. So, you know, the feature here is we have this thing called a GD&T wizard, and it really makes it easy to add PMI to a geometry-only CAD model. All right, let's move forward. What about a prototype? What if I don't have any PMI? What if I just don't care? I just want to measure stuff. Well, we can do that as well. We just, as we showed before, select the features to be measured, but instead of taking that extra step, if you wanted to, if you don't want to, don't add the GD&T. Say, hey, I want these features. I've got a measurement plan, and I want you to measure that. This is very useful when maybe in a prototype workflow, and then when the GD&T gets worked out later, you can bring that model back in and then add that GD&T, or if it's in the MBD, you can import that directly and use that GD&T from the imported MBD. So that's an alternative workflow, but a very common workflow as well. I just want to measure stuff. So this is animating a selection, and then again, it's a video, and this allows you to see that you can look at just parts and segments. By the way, in the plan view on the left-hand side, if I wanted to grab and reorder the basic sequencing, I can just drag and drop, and it reorders automatically. You can see the associativity of the top plane and to the top plane measurement point set, and you can see the associativity in the program view as well. And maybe I want to execute, and I'll show you that in just a second, just the segment of that measurement program. So zoom out a little bit, you can see the path. You can see the cycles of change to the change racks. Okay, I've got it set to where I want it. And let's do, like that view. Well, so you can preview selected part programs, paths for verification, review, and measurement coverage. If you want to animate, you can. If you just want to look at it in static mode, you can do that as well. Let's look at the overall MiCAT Planner benefits and summarize what we've seen. It's a streamlining of processes. It really makes the model-based inspection workflow zing. It improves productivity. It reduces manufacturing costs. Measurement and inspection are part of manufacturing. And anytime you can reduce costs, that's an important issue for anybody who's involved in manufacturing. It enhances traceability because you've got these associativities all the way back to the rules. You've got the associativity back to the particular DME that was used. You've also got the associativity back to the model-based definition. And we think up to a 95% savings in time compared with drawing-based methods. And this is the key thing. When you move to a fully model-based environment, you will only have to supply a single CAD model to inspect the part. And that's important, and that really simplifies the relationship with suppliers as well. Some additional MiCAT Planner benefits. Features and characteristics are directly transferred into the inspection software, reducing the risk of misinterpretation. This is a big one. We all try to be as good as we can, but sometimes we hit the wrong button on the computer when we key that stuff in from the print. CMM configurations can be changed at any point. We didn't show this, but it's very simple to say, oh, I've got this CMM, but it's not available. Can I use that CMM? And you simply say, okay, select it from the pull down, and you're good to go. Enhanced workflow automation, which is very, very important. Time is money these days, and the MiCAT Planner really puts that money back into your pocket. And then, most importantly, maybe is part measurement consistency, because you've got these captured rules that you can apply and reapply in a consistent manner. With that, this is the end of the presentation. I hope there's some questions.
Yeah, we got one or two more coming in. But before I get to that question, just a reminder, we do have a few minutes left, so any of you out there who still have questions, send them to us using the Q&A box, and we will try to get to them in the few minutes that we have left. You mentioned you've talked about modifying the GD&T information with the MiCAT Planner. So one question we had come up is, if you do that, does that actually modify the CAD file? Do you go back and actually change what's in the CAD file?
No, we don't, because we understand that, that's the master definition. When we modify GD&T, we basically modify it within the planner's database. So we don't change the original CAD file, and we haven't been requested to change the original CAD file, but we don't do that, but we do keep track of the changes, and those are very selective and traceable changes that are made within the context of the MiCAT Planner project.
Okay. Can MiCAT be used with other than Mitutoyo CMMs?
That's a question that we'd like to discuss, but it's beyond the scope of this particular webinar.
Okay. And scrolling through, some of these you already addressed. Probe optimization, you kind of actually got into that already. And just scroll, we got to those. You know what? You've already touched on, I think, the questions that we had come in already. We do have a couple of minutes left. Is there anything else that you wanted to demonstrate on MiCAT, or some of the functionality that maybe you didn't feel you'd have time to? I mean, you got about 5 or 6 minutes left if you want to show something else.
Well, you mentioned probe optimization, and I showed a sequence of probes. These are positions and configurations of probes and sensors on a particular CMM. So we have a method that does automatic probe selection, but you may not like what we had the MiCAT Planner think was the best probe. So anytime you need to, you can override those probe selection functions and use whatever probe you deem appropriate. So probe optimization is there, but we always provide those overrides to the operator, to the user, and probe optimization is one of those as well.
Okay. Well, Larry, that looks like it. I don't see any more questions coming in, and the timing is just about right. We're just about at the end of our hour here. So thanks a lot, Larry. Really good information, a lot of good technical stuff in there. Actually, I learned a lot about CMM programming that I didn't know, so there you go. So that is the end of today's webinar, everybody. Larry, again, thanks for explaining the advantages of using software, MiCAT in particular here, for automatically generating your CMM measurement programs. Thanks again, obviously, to all of you who attended. Thank you for joining us. And as I said at the very beginning, there will be an email that will go out tomorrow that will have both a link to a recording of this webinar as well as a PDF of all of Larry's slides. So if you want to go back and review some of the information, you'll have the ability to do that. So again, from all of us here at Quality Digest and, of course, Mitutoyo, have a great day, and we will see you at the next webinar. So long.
Thank you all.